Chapter 8, Lesson 1. In this lesson we'll talk about the concepts of chemical bonding. We're going to talk about three types of bonds. In chemistry there are in general three types of bonds: ionic bonds, covalent, and metallic bonds. And even though if you take a look at the examples, these are examples of each type, the examples visually look pretty similar, but the bonding inside of the elements is very, very different. And in fact, all three of these have drastically different properties. Sucrose, for example, compared to, say, magnesium oxide, compared to copper, drastically different properties. And we'll be able to explain that using the bonding, the theory of bonding. And in all cases, bonding will involve valence electrons. Recall that only the electrons in the highest energy levels are involved in bonding. The internal electrons are actually not involved. So we'll take a look at ionic. Let's do a quick overview of the three, and then we'll take a deeper look at ionic. In ionic bonding, there is a transfer of electrons to form ions, and then there is an electrostatic attraction that holds these ions together. And the electrostatic attraction essentially is the plus and the minus, is the idea. So here we know that sodium has a plus charge, chlorine has a minus charge. In covalent bonding, we have sharing of electrons, and the sharing of electrons occurs usually between nonmetals. This is due to the fact that nonmetals require electrons to become like noble gases, so in both cases they will accept or share. And then finally we'll talk about metallic bonding, which really has a different view. With technically the electrons are what we call delocalized electrons. The valence electrons are allowed to essentially travel throughout the entire metal. They are not confined to a single atom, is the idea. So we'll take a look at these three in detail now. The first thing to say before we go into it, and this will especially apply to ionic bonding and covalent bonding, is that the Octet Rule states that atoms will gain, lose, or share electrons to become like a noble gas. And we've known this, and essentially that's what drives, the Octet Rule drives chemical reactions from the perspective of elements. So here, for example, you see sodium and chlorine. Sodium has just one valence electron in its outer shell. Chlorine has 1, 2, 3, 4, 5, 6, 7 electrons. So sodium will give one up, chlorine will accept one. And in this case, they'll form positive and negative ions, and that's how we form sodium chloride. In the case of nonmetals, you have carbon having 1, 2, 3, 4 of its electrons in the outer shell, hydrogen having 1, and then so hydrogen will share one and carbon will share one, essentially, and that's how we will form CH4, which is a covalent compound. In all cases, both of these follow the Octet Rule. In both the sodium, chlorine, and carbon's case, we have 8 electrons on the outer shell. 1, 2, 3, 4, 5, 6, 7, 8. The only exception is hydrogen and helium. Helium we don't have to worry about because helium does not form any compounds. Hydrogen, however, does, since it only has the one S subshell open. In the first energy level there's only the S subshell. It only needs 2 electrons. Let's take a close look now at ionic bonds. So recall that ionic bonds are between positive and negative ions. This results in solid crystals. There is no ionic compound that's a liquid or a gas at room temperature. All of these have very high melting points. Usually they're formed between a metal and a nonmetal, or between a metal and a polyatomic ion, which, recall, is something like nitrate. They conduct electricity when dissolved in water or when molten, means if you melt. So sodium chloride in the liquid phase, and it takes quite a bit of energy to get it to the liquid phase, but it will conduct electricity. And this is due to the fact that ions are free to move. Just like ions are free to move in the solution phase, they're also free to move whenever they're molten. Ions dissociate and are able to transfer a charge, therefore conduct electricity. Many ionic compounds are soluble in water. Actually, water is a very good solvent for these. but they're not soluble in nonpolar liquids. And we'll get into nonpolar substances later on. But nonpolar simply means it has a different arrangement of electrons around the outside of the molecule. So it does not match the arrangement of ionic substances. That's why it does not dissolve. We're going to take a look at the energetics of ionic bonding. If you recall, we saw that it takes 495 kilojoules per mole to remove an electron from sodium. This is sodium's essentially ionization energy. Ionization energy, which was not too low, not too high, in middle way. And then if you give chlorine an electron, something called electron affinity, you receive 349 kilojoules, because recall electron affinities are negative. So this is electron affinity. These numbers are electron affinity numbers. However, if you take a look, so in the course of sodium and chlorine reacting, sodium gives up an electron, which requires 495. Chlorine accepts an electron, giving up negative 349. If you total these up, if you do 495, just combine them with negative 349, what you see is that you got yourself a positive 146 for the answer, which means it requires energy to form sodium and chlorine, or sodium chloride, we'll say. This is a positive, this is an endothermic process. Now this is very interesting, or very puzzling, because if you take a look, if you ever react sodium with chlorine, here we have a grad cylinder filled with chlorine gas, and then a little bit of sodium in this here bottle. The sodium is placed through actually there's like a little wire that they're using, into the chlorine gas, and notice the violent reaction that occurs. And this powder actually is salt. You're forming sodium chloride. So we see that there's quite a bit of energy released. It's highly exothermic. In fact, the delta H is negative 410.9 kilojoules per mole, which is significant. So the reaction of sodium with chlorine is very exothermic. But we calculated, when we added up the ionization energy and the electron affinities, we calculated a positive number. What this means is there must be something else that we're not accounting for. There must be a third piece to this puzzle. And what the third piece is the electrostatic attraction between the newly formed sodium cation and chloride anion. So what happens, anytime you have a positive and a negative, these essentially attract one another. And when they attract each other, they will come together and bond, and as they do, recall that any bond that forms releases energy. They will release quite a bit of energy. So what happens is, here we have a picture of sodium losing an electron, a chlorine gaining an electron. That is, we said, 146 kilojoules, positive 146 kilojoules. However, when the newly formed cations and anion come together, this bond that forms between them releases negative 410 kilojoules. And that essentially is the third piece of the puzzle, is this attraction that holds them together, the bond that forms between the attraction. So if you take a look, this is a breakdown of the ionic crystal. So in an ionic compound, what you have is you have yourself alternating chloride and sodium ions, essentially arranged in a three-dimensional network, something called a crystal lattice. And here you have strong electrostatic attractions keeping these together, and these are what account for the release of energy. As these bond together, they become very stable, releasing energy. And this we will call lattice energy. This is actually a very important concept that we'll take a quick look into a little more detail. Lattice energy, defined, is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. So we define lattice energy backwards, not when it's bonding, but when it separates. And here's how we write the lattice energy equation. We have sodium chloride, solid, and then if you want to separate them into their ions in the gaseous state, it requires 788 kilojoules per mole, which is an enormous, pretty big number, which means when the opposite happens, when the sodium plus and the chloride minus come together, to form sodium chloride, they will actually release this much, 788 kilojoules, and that's kind of the idea. Let's take a closer look at this idea of lattice energy, because it turns out there's an equation we can write for it and we can quantify it. And this equation is given by something called Coulombs Law. And you may have learned about Coulombs Law in physics, if you've taken physics. So it looks like this. The energy between the ions depend on K is a constant, and then Q1, which is the charge of the first ion, say your positive ion, say sodium, Q2, which is the magnitude of the charge of your second ion, say chloride, and then D is the distance between them. Now, it's a good idea to be able to take a look at an equation and understand what it's saying. What this is saying, essentially, is that your charges here influence the energy directly. So if, say, Q2 were to increase, meaning if the charge goes up, then automatically the energy between them goes up. Or if Q1 increases, the energy between them goes up. Don't worry about K is a constant, so this won't really change. But if you take a look at the bottom here, if the distance between the two decreases, this means we will be dividing by a smaller number, and anytime you divide by a smaller number, your energy goes up. Your overall fraction goes up, essentially. Your answer goes up. So you can see that distance is inversely related to energy. As distance goes down, energy goes up, and conversely, as distance goes down, as distance goes up, energy goes down, is the idea. This is actually very similar. In physics, there's an equation for gravity. The force of gravity is actually, there's a constant, they call it G for the constant, and then they have mass 1, mass 2, and then divided by r squared, which again, r is the distance. So exactly same setup. How strong a gravitational force pulls two bodies together depends on their mass. This is analogous to our charge. So if you have two very massive planets, then they'll attract one another much more strongly than if they're not as massive. In our case, if we have a high charge, you're going to have a much stronger attraction than if you have a low charge. And then the distance between them, you may know from physics, if the two planets are close together, their attraction is much, much greater. That's why, again, r is on the bottom, the distance is on the bottom. This is called the inverse square law. And so interestingly, this works in electrostatics, works with gravity, and it works in many other areas of science and of human life. This law of the closer you get, the stronger the attraction, actually works in many areas, including girls. Okay, so the idea here is, this is essentially kind of a review, but there's an increase with the charge on the ions, but the most important factor of these two, distance, whether distance is important or charge, it turns out that charge is a much more important factor, because charge goes from a +1 in one ion to a +2 in another ion to a +3 in a third ion. So charge goes up very quickly, whereas distance does not vary by as much. So that's kind of the idea. I mean, distances, if you take a look at ions, distances, say across the periodic table, recall, decrease, but not as much as charge. So the fact the charge factor is actually much more important. And you'll see this in just a second. But in general, the higher the lattice energy, the higher the melting point of the ionic compound is. Because the stronger the attractions, the harder it is to break them apart or melt a substance. And then it also increases with the decreasing size of the ions. So it looks like we essentially skipped a spot here, but two of these things. Make sure you understand that the charge makes ionization, or makes lattice energy increase. The distance makes it decrease, is the idea. And here are some examples. If you take a look, all of these in the first column are a +1 and -1. So here's our sodium chloride. And then in all cases, if you take a look at sodium chloride, sodium bromide, sodium iodide, and sodium fluoride, we'll say, as you go down the periodic table, recall that the nonmetals get bigger and bigger and bigger, and you will see that the bigger they get, the smaller the ionization energy gets. This is the distance. And if you go across, these have a +1 -2, or actually +2 -1. In the case of magnesium, +2, chloride -1. These have a +2 -2. And this one, scandium nitride, is +3 -3. And you'll notice there's a big difference. If these are 1,000 or less, these are 2,000 or more. These are 3,000 or more, and this one, notice, is 7,500 kilojoules per mole, an enormous amount of energy that's stored. So you can see how an increase in charge has a big effect, and how a increase in size has not so big of an effect. So why don't we try an example? Arrange the following ionic compounds in order of increasing melting points, and essentially lattice energy. So we want the first one to be with the least lattice energy, the last one with the most lattice energy. For this, we will need to consult the periodic table, so pull out your favorite periodic table, and it looks like we are looking at sodium fluoride, cesium iodide, and calcium oxide. So let's go ahead and mark. So we got sodium fluoride, we got cesium iodide, and we got calcium oxide. So first of all, if you take a look at oxide and calcium, remember calcium has a +2 charge, oxide a -2. So right away we have a +2 -2. And we said charge is a much more important factor. So right away calcium oxide will be last in our case. We'll have the highest lattice energy and highest melting point. So calcium oxide is out here. The question is now between sodium fluoride and between cesium iodide. And the idea here is we want to take a look at which one's smaller. Whichever is smaller, the ions are closer together, and if they're closer together, recall that the energy goes up. So if we take a look, which is smaller, sodium is definitely smaller than cesium, and then fluoride is definitely smaller than iodine. So sodium fluoride being smaller, so your NaF, so sodium fluoride, would roughly look maybe like this, whereas your cesium iodide is going to look, cesium by itself is a bigger atom, and so is iodine. So the distance between them here is smaller than the distance between them here. Therefore, the attraction is stronger in the smaller distance, because recall the equation said the distance gives you an increasing lattice energy. So we'll actually put them. We'll have to put, since sodium fluoride has a higher lattice energy, we'll put them right in front of calcium oxide. And then cesium iodide has the least lattice energy, is the idea. So here would be the arrangement. And a quick summary here. What we could do is we've summarized and accounted for the energetics. So what you see is this is ionization energy of sodium. If you want to ionize sodium, this is the electron affinity of chlorine. Notice there's this gap, but this gap is more than bridged by this lattice energy. So this is essentially what allowed the total difference between here and here to be a decrease in energy. So this is just a summary of the energetics, and not as big a deal to understand this diagram, but this essentially summarizes everything we've talked about. And this also explains the Octet Rule in terms of, if you take a look at sodium, remember we said there's a huge jump between losing the first and the second electron. And in the case of sodium, you really only find sodium with a +1 charge in nature. You don't find sodium with a +2 charge or anything else. Sodium always has a +1 charge, and that's because making it into a +2 charge involves an enormous amount of energy, and that energy cannot be overcome by the lattice energy. Lattice energies, whenever the substance forms, cannot overcome or cannot compensate for the required energy to form that higher charge, and that's essentially the idea. Okay, and we'll stop here for lesson